Hi everybody, this is lesson 3.3, probabilities involving and not. Alright, let's read the specific objectives. So in this lesson, students will understand that compound probability problems can involve independent or dependent events. Compound probabilities involving independent events can be solved using a simple formula. The probability of an event not happening is called the complement of that event and can be easily determined from the probability of the event itself. Students will be able to calculate probabilities involving independent events and calculate probabilities involving an event complement. All right, so in the lessons prior to this one, we did define a notion of probability and probability as being a chance of something happening. And on the previous lesson, 3.2, we discussed the probability of the event involving an OR, where what we call this kind of like an addition rule of probability. The probability of A or B is going to be probability of A plus probability of B minus probability that the two events happening simultaneously. So we're going to continue talking about compound events. So a compound probability, as you see here, sort of a little reminder what it is. Problem involves figuring out probability involving in multiples or repeated events, such as multiple flipping of a coin, the genders of children, and so on. In each of those scenarios, the probability of any outcome was 50%. All right, let's review those concepts. Suppose the two coins are flipped. What is the probability that the both lands heads? Can we review that? I'll give you a moment. Alrighty, so how do you approach this? Well, we need to write down all the possible outcomes of what happens when you flip two coins. So it could be, both of them could be heads. One of them could be heads and the other one would be tail. The first one could be tail and the second one would be the heads, or both of them are tails. So there are four equally likely events. And what is the probability that you have heads? Well, it's 1 out of 4 choices, or 25%. Okay? Alrighty, looking at that, the same outcome, what would be the probability that two coins do not land the same way? Meaning that one of them are heads and the other one is tail. What are the chances for that? Just look at this again and write down your fraction and then express that as a percent. I'll give you a moment. Alright, so let's review. There are two events possible out of 4 where one of the coins is heads and the other one is tails. These two events are different because each coin lands differently, so those considered different events. There are 2 of them out of the 4 possible chances. So part C is reminding ourselves, what is the fundamental law of probability? I mean, we know the probability is a fraction. Now, how do we define it again? So probability of an event equals to what? I'll give you a couple of choices for you to choose from. Okay? And let's review. So probability of the event is number of ways E can occur Alright, so in other words, we're measuring this E, how many times can it happen, divided by the total number of possibilities. Alright, so it is always going to be a proper fraction, or it is equal to either 0 or 100% or anything in between. Alright, so as you can see in the previous examples, there are 4 different outcomes, and if we're measuring some kind of event which is clearly stated, then that will go in the numerator. So for the first example, what was the probability that both lands heads? Well, there's one such event, right? That's possible out of 4. Well, for the second one, we had 2 different outcomes, heads, tails, or tails, heads, out of 4 possibilities. Okay, so that's just a notion of the probability. So let's explore it a little bit more. Sometimes it's difficult to apply this law directly because the total number of possibilities can be very large. To begin exploring this challenge, we'll consider probability in the context of games. A friend of yours likes to gamble. He's offering the opportunity to play a game that costs $1 to play. The game involves 5 coins tossed at the same time, right? We're going to assume that all of those 5 coins are fair, so there's a 50% chance of it being either heads or tail. If all coins land heads, he loses his $1. If anything else happens, then he wins $1 and get his original $1 back. Okay? All right, we can make a picture. All right, so you have 5 coins. Each one of them going to be either heads or tail, and he is going to win as long as not all of them are landing the same way. So either all of them are heads or all of them are tail. Oh, actually, it just says only if they all, if all coins land heads, that's the only time that he loses. If anything else happens, then he wins $1, right? So there's only one possible chance that he can lose. Part D. Part D of the introductory question: is this a fair game, an advantageous game, or disadvantageous game from your friend's standpoint? So I'll give you a moment, just think about it, and you have 3 choices. All right, is it a fair, is it advantageous, or disadvantageous game? What do you think? All right. Okay, so let's review. So here we're not actually trying to do any calculation. We just want to think of this intuitively. Would you play this game? I would, because I have a lot of chances of actually winning, and I have a very little chance of losing. So would I say it is a fair? Well, it definitely not disadvantageous game. I would I call it a fair game? Well, what does fair mean? So fair means, let's define the word fair. Fair means that it is not advantageous to either of the players. All right, but this game sounds more like I'm going to win more likely than I'm going to lose. So I wouldn't call it fair, because it's not fair to the player I'm playing against, right? Because I'm more likely to win it. So I would call this fair advantageous to me. Advantageous, right? Advantageous to me. Just because I have a more likely times that I'm going to win it. Now, how about if your friend were to apply his savings to this game, playing it over and over again? Would it gradually accumulate money or gradually lose the money? What do you think? I'll give you a moment. I mean, if the player is advantageous to me, so it says if your friend were to apply his savings to this game. Oh, the friend in the game likes to gamble, correct? Oh yeah, the friend likes to gamble and he is offered to play this game. Definitely he will win eventually, right? I mean, he'll be winning more often than losing, right? Because you can see that there are many outcomes to this game. There are many outcomes, you know, because you're throwing 5 coins. They can be either all heads, they can be all tails. Some of them can be heads, some of them can be tails. There are lots and lots and lots of possibilities, but there's only one possibility of him losing out of many winning combinations. So he'll eventually win the money. Yep. All right, so now how about the second part of that question? If the rules of the game were reversed and your friend only won $1 if all 5 coins turn heads, would your friend accumulate money or lose the money if you play the game repeatedly? Okay, so now the idea is the only time the player would win if all of them are heads. So what happens in this case? Will we win or lose? What do you think? I'll give you a moment. Well, now we only have one chance of winning, right? There's only one chance of winning out of many possibilities. Just for like an extra point, would you think about like how many different outcomes are there? And look, you see, we started the class today with the what is it? 2 coins, right? And there are 4 different outcomes when you throw in 2 coins. Like if you throw in 2 coins, there are 4 possible combination that can possible. All right, remember last class, I think the very first one in this chapter, we talk about triplets, like kids and genders, right? And then we got like when we had boy, 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 girl, boy, that thing, you remember? When there were 3 different siblings, what is the total number of possibilities of, different biological genders? And if you recall, it was 8. So basically when you have one coin, which is just like, one child, biological gender can be boy or girl, but one coin it can be heads or tail. So one coin, there are 2 possibilities. All right, when you have 2 coins, there are 4 possibilities. When there are 3 coins, it's like 3 siblings. You can look back in that lesson, you'll see there are 8 different possibilities, all different. Boy, 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 girl, boy, boy, girl, 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 boy, girl, and so on. We wrote them all out. There are 8. Same thing if heads, tails, heads, tail, heads, tail, all together we'll be able to get 8. Do you see the pattern? What if there are 4 coins? You see the pattern? I'll give you a moment. Select a choice. How many do you think? All right, if you see the pattern, it actually doubles. Like our very first lesson, doubling. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 possibilities with the 4 coins. You can write them all out, by the way. You'll get 16 possible answers. 16 possible combination. If you got 5 coins, that's exactly what we're looking for. How many possibilities are there? Double it again and you get 32. There are 32 possibilities of winning. All right, so would you play the game if you had one out of 32 chances of winning? And what are you winning? You're only winning $1. Oops, only winning $1. Otherwise, you lose $1. So what's going to happen? I'm not going to play that game. I'm not going to recommend my friend play a game because there are very low chances of winning. So the friend will be losing the money eventually. You understand it because there's a low chance of winning. Now I suppose the rules of the game I change again. It still costs $1 to play the game, and you only win if all 5 coins land heads again. However, instead of winning $1, you're winning a $20 bill. All right. So now there are 1 out of 32 chances of winning $20 for every dollar played. So what do you think? Is this game advantageous or disadvantageous to the player? If your friend plays the game repeatedly, will your friend lose the money or accumulate the money over time? This is a little harder question. I still want you to give your intuition, so you can go ahead and express what you feel going to happen. And now if we review this again, you don't have to give a numerical answer. You want to just think about an intuition. So you still get 1 out of 32 chances of winning $20 in this case. So it's still a low chance, but there's a higher winnings, right? So if we try to kind of conceptualize it, so the chance of winning $20 is I put 20%. $20 is going to be 1 out of 32 which is about 3% if you divide. All right. However, what are you winning? You're winning $20 for $1 invested. So $1 invested for $20 won. This represents only 5%. But your chances of winning are only 3%, that are lower than your return on investment. So when that happens mathematically, you can show that eventually over time, the player will still gonna lose. All right, so the player is still going to lose over time. Listen, again, we're not in probability class, so we don't expect, to calculate, this very deeply. But I do just want you to understand that when you have a low chance of winning, even if you have a higher investment, it's still low. All right, so it's still unlikely that the player is going to accumulate anything. Things will change a little bit more if you're winning, let's say, $100. Then your return of the investment is, 1%. So that way there is a chance of winning more than what you are investing. But this is one of the ways that you can compare the odds. All right, so now let's go to the type of questions that you expected to be able to calculate in this class, and that is dealing with the events that are independent. So far what we have seen right now are independent events. Flipping a coin is an independent event followed by another coin. Biological genders of children, that's also independent events. So now the time has come to define what it means to be independent. So two events are considered independent if the outcome of one does not affect the other. So the way you can understand this is like this. If one of the siblings is a boy, and then someone else coming along, right, another kid, does the probability that the biological gender of that next sibling is going to be a boy or girl, is it in any way related to the fact that the other siblings of the other gender? No, because this event is particularly independent of anything that has happened before. All right, it doesn't influence it. The same way with flipping a coin. If the first time you got tails, and then the next time you flip it, it doesn't matter that it was tails before. The probability that it had those tails will not change. So those events are independent. So looking at that definition, we're going to look at a couple of scenarios, and the only thing you need to choose is whether the events are independent or dependent. So let's start. You have two separate dice are rolled. All right, and you got two separate. Remember, die is the is a cube that has numbers reading from 1 to 6. Okay, we're gonna assume it's a fair die. All right, so two of them are rolled. Is the fact that one of them ends up landing on 1 or 3 or 6 or whatever, does it affect the other die? Is one somehow influence the outcome of the other? And if they do influence each other, then write the term dependent. And if not, write independent. I'll give you a moment. Well, these are classical example of the independent event. Doesn't matter what one is, the other one is completely by itself. Understand? One does not influence the other. How about the deck of cards? We've seen the deck of cards last class. So if you take a card from a deck, you set it aside, all right, and then you take a second card from a smaller deck because one card already been taken out. Is the fact that you get a particular outcome the second time around, does it change based on the fact that you got some other card at first? And here it is, we don't replace it back, we set it aside. So think about it. I'll give you a moment. Are these two events dependent or independent? Well, in this case, actually, this is considered to be dependent event. And to understand this, Remember, each card, if you get it from a deck of cards, is equally likely. So you pick one up, you have 1 out of 52 possibilities, correct? That would be the first card. Probability of the first card is 1 out of 52. Probability of what the second card would be, whatever it is. Now, what you got, whatever it is, let's say it is a probability that it is any card in the deck. There are 52. Each one is equal likely. The second one is you selecting one, but now you have a deck of only 51 cards left, so the probability is becoming a little bit higher because you got the less cards in the deck. So it does change. However, for part C, if the card is drawn from a full deck and then another card is drawn from a different full deck, both of them have 52 cards, does the probability of, whatever you get in the first deck influence probability on the second deck if you don't shuffle them in any way? What do you think? Well, in this case, the events are completely independent. One does not influence the other. All right, so you just got to ask yourself, does probability of one thing influence a probability on the other? If they influence, you say dependent, and if they are not influenced, you say independent. So let's look at the part D. Whether a person is left-handed and whether the same person's hair is blonde. Okay, is the fact that someone's hair is blonde, is it somehow related to the fact that the person is left-handed? And if they are related, you say the events are dependent, and if not, you say they're independent. So what do you think? All right, so the answer here is that they are independent. It has not been proven that being a left-handed somehow influenced the hair color. So here goes. It's independent. What about part E? Whether a person is male and whether the same person is 6 feet tall. Is the height influenced by the biological gender? What do you think? If they are influenced, then the events are dependent. And if not influenced, then you say they are independent. I'll give you a choice. Well, from biology, we know that males, as a biological gender, on average have higher height than female. It's a biological fact. And therefore, if we know that the person is male, it will influence their average height. Okay, so those two events are definitely dependent. That has been shown. It's a fact that there is a relationship between height and a biological gender. Part F, whether or not class is a math class and whether or not the classroom has windows. Is there any relationship between having windows in a math classroom and whether it's a math classroom or not a math classroom? Are these dependent or independent events? I'll give you a moment. Well, these are definitely independent. What does it have to do with, the fact that there are windows? Well, not every classroom has windows. You might be in a basement and that doesn't have any windows, but what does it have to do with the subject, right? So these events are particularly independent. And the last one, whether or not a professor is a math professor and whether or not the same professor likes movies involving robots. So what do you think? So here the answers will vary. There might be the fact that someone is a math professor and they studied mathematics, so they like, I don't know, maybe some kind of structure. Maybe they were applied mathematician and then they also like physics somehow. So there might be some dependency, or you might say it doesn't matter, okay? Being a math professor doesn't influence you liking robots or whatever it is. Okay, so here it's not clear, okay? More context is needed about the person. So maybe then we can find the dependency. All right, so here it vary, okay? The answers will vary, so whatever you chose, both is acceptable. However, when we know that the two events are independent, then the compound probability, compound means that you have more than one thing happening, of that event can be calculated according to a simple formula. Use your experience from the example you've seen involving flipped coins to finish a formula that begins the probability that it is A and B equals to what? So if you recall, remember when we got probability that you had, let's say, 2 heads when you flip coins? Remember the answer? It was 1 out of 4. But probability of each head, like if you get heads on first try, is 1/2, and the probability that you get head on the other try is also 1/2. So then what's the probability that heads followed by another heads? How are these two related to that? What operation? Is it addition, multiplication, division, subtraction? What is it? Well, if you check this out, this is going to be actually multiplication. All right, so probability that you have heads, it's the probability of heads and another head. So it's 1/2 multiplied by 1/2. If you check this out, when you do 1/2 multiplied by 1/2, you basically, when you multiply 2 times 2, that gives you the total number of possibilities. Heads, 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 tails, tail, heads, tail, tail. And 1 times 1 gives us 1 outcome, heads, heads. So the multiplication will allow us to find probability of what we call independent events. So this is something that we're going to use. So probability that you have A and a B, so when you see that combination, A and B, compared to what we did in the other lesson, which was probability of A or B. So probability of those two outcomes is going to be probability of A multiplied by the probability of B. So it's called a multiplication rule of probability. And it applies to independent events only. When the events are dependent, it's a little more complicated slightly, but that's not part of our curriculum, so you don't have to worry about it. So whenever you ask to calculate the probability of AND, you can rest assured that the events that you got are independent. So check this out. Let's do one together, and then I'll give you a moment to do the other ones. So you got 4 coins are flipped. Find a probability that all 4 coins lands tails. So probability that you got T and T and T and another T. All right, we already said many times that the probability that one coin is heads or tails does not influence probability that the other one is heads or tails. So using the notion of probability, there are 4 events. Okay, so whether it's 4, 5, 6, a million events, it doesn't matter. If they're independent, then to find a probability, we have to multiply probability of each event. Now, what's the probability that you got a tail? Well, that's 1/2. So we have 4 such events, so we take 1/2, multiplied by 1/2, multiplied by 1/2, and you're multiplying it by 1/2. Notice what happens in this case. When you multiply 2 times 2 times 2 4 times, that gives you 16, while you have only 1 success, meaning that all of them ends up being tail. We've done this already, by the way, before, when we made a list early in the lesson. You see, the 4 coins, 16 possibilities, and there's 1 out of 16 is the success. Now we make it a little bit more systematic, is when, if we know the probability of each event, you don't even have to count this. You just go ahead and you multiply the probability 4 times, and you get the answer of 1/16. Remember, you're not adding, you're multiplying. All right, so 2 dice, 1 red and 1 green are rolled. Find probability that the red die rolls a 6 and the green die rolls a 1. So you just have 2 dice. Okay, so probability that one of them, let's draw it. One of them rolls a 6. 1, 2, 3, 4, 5, 6. And the other one, the green one, rolls a 1. Can even highlight you the colors. So one of them is green. All right, and the other one is red. Okay, so what's the probability of that? The die are independent events. So what's the probability that it is a 6? What is it? What's the probability that it is a 1? And then take those two probability and multiply. I'll give you a moment. All right, so let's review. So probability that you get a 6 is 1 out of 6 chances. Probability that you get 1 is also 1 out of 6. So you multiply these, there's 1 success divided by 36 different outcomes. All right, there are 36 outcomes. You can kind of understand this by thinking about, you know, you got 3 outcomes. I mean, there are there are 6 outcomes that you have 1 coin to, I mean 1 die to be something, then you got another 6 there, you pair them up with each other, so altogether you're gonna have 36 possibilities and only one of them is a success. You understand what I'm doing? Let me just draw this here. You see, so these are the possibilities. I want you to understand why you're multiplying it. Check this out. So these are all the possible scenarios that can happen. If you pair them up like this, here there are 6 outcomes, then you have another 6 outcomes, and then another 6 outcomes. You see, I'm distributing it, so altogether there's going to be 36 possibilities. I understand it looks like a mess, but I want you to see the multiplication happening here. Alright, so there are 36 different outcomes and only one of them is a success, which would be 6 on that one and 1 on that one. So it's 1 out of 36 possibilities. So it's much easier to just apply the rule like that. Let's try another one. A card is drawn from each of the 2 separate decks. Find a probability that the first card is a heart. So probability that one of the cards is a heart. And the second card is black. So probability that it's a heart. And the second word is a black card. And when it comes to colors, there are half of them, I guess, that are black, and there is half of them that are red. Okay, so we'll assume that half black and half red. So what would be the probability that the first card is a heart and the second card is a black card? I'll give you a moment. Let's find a probability of each. So probability that it is a heart is 1 out of 4 because there are 4 suits. Okay, heart, spades, diamond, 4 of them, and the heart is 1 out of 4 possibilities. Probability that's a black is 1/2. You multiply them, you get 1 over 8. Do not forget, you multiply them across. Alrighty, let's do another one. A card is drawn from each of the 2 separate decks. Find the probability that the first card is an ace and the second card is a queen of spades. I think last class I gave you the picture of the deck of cards, so I'm giving you it here again. Alright, you can also look it up online, just get a picture of deck of cards. Now you can see half of them are red, half of them are black. There are, you know, 4 different suits, there are 4 aces, there are 3 faces within each suit, there are 3 times 4, which is 12 faces, and so on. Alright, so looking at that question, we need to know that information in order to then answer the question. You do the multiplication rule. So what's the probability that the first card is an ace and the second card is the queen of spades? I'm not going to even try to draw spades. Okay, I'm not good at this, so I'm just going to write it like that, queen of spades. And we're going to go ahead and write each probability and then multiply it. I'll give you a moment and then select a choice. So let's review. So probability that it is an ace. How many aces we got? We got 4 out of 52. Probability that it is an ace is 4 out of 52, which reduces to 1 out of 13. There's 1 ace within each suit. How many queens of spades are there? Well, there's only 1 out of the 52 cards. You multiply it there, you multiply 13 times 52, and you get 676. A low chance for that happening. All right, let's take a look at something that's not cards, but percentages. It says approximately 60% of student population of BMCC is female. A survey is conducted in which 2 calls are randomly made to 2 different BMCC students. What is the approximate probability that both of the students receive a call were female? So probability that it is F and F. But we're not talking about biological genders of kids. We're talking about population at BMCC. So here, what you want to know, what's the probability that the first student that was called as the female multiplied by the probability that the second student is a female, just like that, right? You look at each of them as probabilities, okay? So what's the probability that, a student will be female? That depends on the percentage. It's 60%. What is 60%? It's 60 out of 100, which you can write it as 6 out of 10. You can write this as 3 over 5. All of these are going to be correct results, okay? So then, what's the probability that the other student is a female? The same thing. All right, so there are two. I mean, you can use fractions if you like, and then just do it, multiply it across the simplified version. 9 out of 45. Okay, and 9 out of 45 would be equal to, it's not 45, I'm sorry, it's 9 out of 25. And 9 divided by 25 gives us 36%. All right, or you can work with the decimals. That's also good. I'll recommend even using decimals. So it's 0.6 or 0.60 multiplied by another 0.60. That gives you 0.36 or 36%. Just be careful when you do this calculation. You either use decimals or fractions, but don't use percent. So don't multiply 60 times 60. It's okay, you could do that, but then you would say you have to remember that it's a percent, so it will be 3600%, which then 3600 as a number, which then you convert into percent will be 36. So it is recommended that you would either keep them as decimals or as fractions. All right, but again, the probability makes sense that it goes down since you are looking at 2 separate events, so it is decreasing. All right, so the last thing for today is to talk about probability involving not. We normally think of probability in terms of the likelihood of an event happening. However, one might be concerned with the likelihood of an event not happening. Use your understanding of probability and your intuition to calculate the following probabilities. So a card is drawn from a deck. What's the probability that it's not the Queen of Spades? So how would you answer that? All right, so let's review. Well, there's only one Queen of Spades that are there. So the fact that it's not a Queen of Spades, it would be all the other cards, correct? There's 51 out of 52. Okay, that's it. So it's easier to just say, okay, what's the probability that it is a Queen of Spades? And then just take it away. Here's another one. According to The Economist magazine, the chance of any given plane crashes is currently considered to be 1 in 10 million. If you board a plane, what's the probability that you will land safely? Well, safely means that it's 1 taking away from 10 million. All right, so what would be 10 million? Well, 10 million is this. So the probability that you'll land safely is going to be, gotta subtract one bad chance of that not being safely. So it would be 9,999,999 out of 10 million, which is a very high percent. All right, so it's almost, we can leave it like that, right? It's almost 100%. So the set of alternative outcomes to any given event is called a complement of the event. The notation often used to denote the complement of any event as E complement, like that with the EC. A die is thrown, event E, the result is odd. For each of these events, describe in words what the complement is. So if the event is odd, what would be the complement? And complement is the alternative event, right? The other outcome. So if the event is the odd number, what would be the alternative outcome? I'll give you a moment. Well, the other possibility that the result is even, correct? Odd would be 1, 3, 5. The even would be 2, 4, 6. All right, so that's the complement. B, a card is drawn randomly from a 52 deck. If the event card is a diamond, then the complement would be what? That it's not a diamond, which would be either we got the spade. Last time I think I forgot to mention club, just blanked out for a moment, and the other one is heart. All right, which is, by the way, is going to be 3 other suits. C, a U.S. citizen who is eligible to vote is chosen from a random. E is the person is over 50 and female. So what would be the other complement of the population? I'll give you a moment. Well, that will be all male of regardless the age, correct? Or, we gotta say or, the other group is going to be female and under 50 but over 18. So between 18 and 50. Between 18 and 15, so that means 18 to 49 years old. Females and all the males, that would be complement. So you understand, complement is just the other part of the outcomes. Derive a formula for the probability for the complementary events. In other words, what would that be? Well, you see, it's the probability of a complement is basically going to be the other part of the probability. So for example, if probability that it rains is, let's say, 30%, then probability of a complement that it does not rain, would be 70%, correct? So it's 30 versus 70. So probability together has to add up to 100%. Do you agree? So if something happens, probability that it does not happen would be the other percentage. So probability of complement is defined as 1 minus probability. So it's 1 minus probability of the original event. Okay? All right, and now last question for today. We got Bob and Maria are going on a trip. They will be going for 4 days. They have a garden of tomato plants that must get water at least once during that week, or their tomato plants will die. The weather forecast predicts 50% chance of rain every day for the entire week. So Bob feels confident that their plants will get water at least once and survive. There's a 94% chance it will rain at least once, and that's good enough odds for me, he tells her. But Maria is not so sure. By her reasoning, there are 5 possibilities that it will rain: 0, 1, 2, or 3, or all 4 days. All right, so those are the 5 outcomes that she writes. And since the possibility of it's raining 0 days is 1 out of 5, she's saying there's a 20% chance that the plants will die. She thinks that the chance is too high and that they should hire someone to water their garden. So who is right? Okay, so we're not sure where the Bob is getting 94% chance. It's kind of, not clear where Maria is getting 20%. She's listing the possibilities. So let's think about this. So we got 4 days. Let's say Monday, Tuesday, Wednesday, Thursday, and that's it. All right, so it's going to be 50% chance of rain for each of those days. All right. So when will the plants die? If it's going to not rain at all, right? On all days. So what is the probability that it never rains? Can we answer that question? Does the probability that it rains on Monday influence probability that it rains on Tuesday? Let's assume they not. That we just know that they all separate days and it can rain or not, so we don't know. We assume that they are not, one day does not influence the other. So if we assume that, then probability that it never rains is probability that it does not rain on Monday, multiply by the probability that it does not rain. I'm just gonna write like this: does not rain on Tuesday, and then we got times probability that it does not rain on Wednesday times the probability that it does not rain on Thursday, and probability that it does not rain is going to be 1/2 on each day, correct? So probability that it never rains at all is going to be 1/2 multiplied by 1/2, which is 1/8, correct? It's 1/8. 1 divided by 8 is, it's not 1/8, I'm sorry, it's 1/16. 1/16 is 0.0625, which is 6.25%. So probability that it does not rain at all, okay, is going to be 6.25%. So that's the only probability that the plant's actually going to die because it never rained. Now, what would be the complement of that event? The complement of that event is the probability that it's going to rain at least once, correct? That would be the complement, which will be 1 minus 6.25%, or I would say 100% minus 6.25%, and that gives us 93.75, which is about 94%, and that's exactly what Bob got, which is high probability. So I guess there's no need to hire anybody. All right, Maria assumed that those days are dependent somehow, so that's why 20% is not accurate. It's only 6.25% that it's never going to rain, not 1 out of 4, okay? Because these events are dependent. All right, so don't get too thrown off with this. I understand the past 2 lessons were quite hard, okay? Just practice with this ideas. When we talk about events involving an or, you add the probabilities together, minus you subtract any overlap. When you talk about independent events, and like in this case, you multiply the probability. That's what you want to keep in mind. Alrighty? And on that, we're going to finish the lesson.